Okay, meeting's being recording. Thanks for accepting the invitation to speak at our seminar, Florent. It's a pleasure to have you from Texas A&M, and that's it. So please go. You have the floor.
Right. Thanks, Braga. So yeah, thanks for inviting me to speak at this seminar. I think I might be able to place the word operator at some point in my talk, but it's not going to be a work on operators per se. But since I expect the audience to be familiar with descriptive set theory and maybe logic, I want to talk about something that has, that uses some technique from descriptive set theory for a geometric problem. So this is a joint work with Gilles Lancien from Besançon, Pavlos Motakis, who is in York University now, and Thomas Schlumpfresh from Texas A&M. And so what I want to talk about it's about universality result in the metric setting. So, but let me introduce first a couple of results about universality, but in the Banach space setting. Okay, so so there is an old result of Banach and Mazur, which says the following thing. So if you take a separable Banach space, and well, you can always embed a separable Banach space linearly and isometrically into C of 0, 1. So the Banach space of continuous functions on the interval 0, 1. Okay, so here the embedding is a linear embedding. Okay, so and it's isometric, so it's a linear isometric. Now the space C of 0, 1, obviously it's a separable Banach space. So you have a separable Banach space that contains an isometric, linear isometric copy of every separable Banach space. Okay, so a space with this property, and I'm not gonna worry too much about being isometric, but isomorphic would be fine, will be said to be a universal Banach space. So we say that Y, so Y, let's say, is a Banach space, but it could be a metric space. Well, here, in this case, for the first definition, it's going to be a Banach space, is universal for a class C of Banach spaces if, so for every Banach space in the class C, X embeds linearly and isomorphically into the Banach space Y. So you have a bounded linear operator into Y, which has a continuous inverse. Okay, just a linear embedding. Okay, and so what the Banach-Mazur theorem says is that a Banach space Y is universal for the class, which I will denote by set for separable Banach spaces, if and only if so it contains an isomorphic copy of C of 0, 1. Okay. So this is completely obvious once you know Banach-Mazur theorem. Okay. So if you want to show that a Banach space is universal for the class of separable Banach spaces, the only thing you have to worry about is finding a copy of C01, for instance, because then you would get the other ones for free. So I will denote by SR the following class. So the class of separable and reflexive Banach spaces. Okay. And so here, I think I said it already, but you have a universal space for the class separable that belongs to the class. Okay, C of 0 is separable. So now there is a natural question, which is if you look at these smaller classes of Banach spaces, so separable and reflexive, can you find a universal Banach space that belongs to this class as well, that is separable and reflexive? Okay. Well, it turns out that Szlenk in 1968 showed that this is not possible because he proved the following result, which says that if Y is universal for the class of separable and reflexive Banach spaces, then the dual of Y has to be non-separable. So this implies that that Y cannot be separable and reflexive. Okay, and so there is no hope to find a universal space for the class SR, which belongs to the class SR. And the tool that Szlenk introduced for this was the Szlenk index, which is an ordinal index, which is related to filling the dual unit ball of a Banach space with weak star open sets. Okay. So the Szlenk index has had a tremendous impact in the theory of nonlinear classification of Banach spaces, synthetic theory. So this was a very this is a very important tool. Okay. And in a couple of years later, Bourgain, so this is in 1980, so in a very short paper in the Proceedings of the AMS, showed the following thing. So if Y is universal for the class of separable and reflexive Banach spaces, then Y is universal for the class of separable Banach spaces. Okay. So this is a strong refinement of Szlenk results. So you have the class of separable and reflexive Banach spaces, which is obviously included in the class of separable Banach spaces. And what Bourgain says is that if a Banach space contains an isomorphic copy of all the spaces in this class here, then you have to contain C of 0, 1. So you have to contain all the Banach spaces. And what he showed is that you have to contain C of 0, 1. Okay. So this is a quite remarkable result, I think, because of course none of the separable reflexive Banach spaces can contain C of 0, 1 because they're reflexive. But it says that all of them, I mean, when you look at them all together, they all contain some fragments or some pieces of C01, and containing all of them isomorphically allows you to recover C of 0, 1. Okay, so there is some reconstruction of C of 0, 1, if you want to think of it like that, out of some pieces that you can grab in all the separable and reflexive Banach spaces. Okay, so this is definitely something that I mean, there is something deep going on here, and the tool that Bourgain used to do that. So this is Bourgain's index theory for basic sequences. So I will explain what is Bourgain's approach, because our work is heavily influenced by Bourgain's index theory, and our idea was, okay, how can we make sense of this in a nonlinear setting? Okay, And I will explain what was, what was our solution to this philosophical question. So, and of course, the basis that was important here for Bourgain was the fact that the C01 as a basis. Okay, so for every basic sequence, you can define an index with certain properties, and here you're gonna look at the index for C of 01, but it's not about the space. The index is not about a space; it's about a basic sequence or a basis of the space. Okay, but I'll explain this very early days in a second. Okay, so now what about universality in the nonlinear setting? So let me recall.
I have a question.
Yes. Yes.
If you have two Banach spaces and they contain the same set of reflexive subspaces, what do you know about the Banach spaces? So if they have the same finite dimensional subspaces, then I guess they're mutually finitely representable. And if they contain the same subspaces, then they contain each other, so they're mutually embeddable. What happens if you pick something in the middle and you just ask that they contain the same reflexive Banach subspaces?
Okay.
If it's a crazy question or not a good
question.
No,
that's a good question. I don't know about that, but so if you contain,
we can come back to it. I just thought I'd forget my question.
I don't have a current example. Yeah, let's go back to this later. But that's a good question. I don't know about that actually. So yeah, let's delay this to let's postpone this to the end of the talk. All right. So let me define nonlinear the nonlinear embeddings that I want to consider in this talk. So if you have two metric spaces, X and Y, I'm going to say that X coarsely embeds into Y, and I'm going to use this notation. If there exist two control functions, so rho and omega, non-decreasing, and a map f from X to Y, such that for every x, y in X, I can control the distance between the images with these two control functions. So there is a compression function and an expansion function. So the compression function is rho and the expansion function is omega. And so if I don't write any conditions on rho and omega, I'm not saying much. And what I want is that the compression function rho goes to infinity with t. Okay. So this is kind of a dual notion to uniform embeddings. Uniform embeddings, you want omega to go to 0 when the distances go to 0. So here you want the compression to go to infinity when t goes to infinity. So why do we care about this? Well, this coarse geometry, coarse embeddings have a lot of applications in non-commutative geometry, topology, things related to Bourgain conjecture. So these embeddings were introduced by Gromov, and they turned out to be extremely important. Okay. And so what you might be a little bit most familiar with, if rho is at least some multiple of t, and omega at most, let's say, some other multiple of t. So then what we have, so here we just have, so here we would have essentially less than bt, b times the distance between x and y, and here we would have at most the distance between x and y over A. So what we have is the notion of bi-Lipschitz embeddings. Okay, which is a much stronger requirement than a coarse embedding. Okay, of course, a bi-Lipschitz embedding is a coarse embedding because the compression function goes to infinity as a linear function. All right. So I'm going to look at these two type of embeddings, and I'm going to look at universal results in the metric category, so metric spaces for coarse embeddings and for bi-Lipschitz embeddings. So there is a result that is important for us here, which is a result of Aaroni, which says the following thing. So for every, every separable metric space admits a bi-Lipschitz embedding into the space C0. Okay. So the Banach space of this is a sequence space, so much smaller than C of 0, 1 of sequences going to 0. Okay, with the supranorm. And we actually know the distortion. So the distortion, which is just the product of the constant A and B here, this constant can actually be taken to be 2. So this was not in Aaroni's original paper, but this was shown to be true by Carlton and Lancien in 2008, I believe. So this is fairly recent, the optimal, and this is optimal. Okay, 2 is the best you can hope for. But this is just a side remark. It doesn't play any role in what I want to talk about today. Okay. So because of Aaroni's theorem, I'm going to say that a metric space is Lipschitzly or so coarsely universal. So the definition is self-explanatory here, which means that Y will contain a bi-Lipschitz copy of every every space in the class that you want to consider. But if I'm interested in the class of separable metric spaces, okay, showing that metric space is Lipschitzly or coarse universal for the class of separable metric spaces, I just need to show that C0 by Lipschitzly embeds into Y or coarsely embeds into Y. Okay. Because of Aaroni's theorem, right? So, so now you can try to ask universality questions in the purely metric context. Okay. So of course, Szlenk index, the Szlenk theorem in the metric context doesn't make much sense. I mean, what is a reflexive metric space? I mean, I think there are definitions about that, but I'm not sure how it would fit in the type of things we're trying to do. So we will be concerned with finding metric analogs of Bourgain's theorem. And one theorem that I want to state is the following. So if a metric space, so separable, and Lipschitz or coarsely universal for the following class, so let me write the class like this: separable, reflexive, so this is a class of Banach spaces, plus asymptotic C0. Okay. Then Y, so then C0 embeds. So if I started with a Lipschitz universal statement, it's going to embed Lipschitzly. And if I start with the coarse universal statement, it's going to embed coarsely into Y. Okay. So this is saying that if so, of course, none of the spaces in this class contains C0 Lipschitzly or coarsely. Okay, they're reflexive. So there is a result of Carlton from 2007, which says that C0 does not embed coarsely into any reflexive Banach space. Okay, so here you have a class of Banach spaces. None of them contain C0, but again, if all the spaces in this class Lipschitz or coarsely embed into a metric space, then it will force the metric space to contain either a Lipschitz or a coarse copy of C0. Okay. So the proof of the theorem. I have to mention here that this refines a result of Braga, who showed that if a metric space is coarsely universal for the class of separable and reflexive Banach spaces, then it contains C0. Okay. But here we have a strictly smaller class of Banach spaces. So what are the ingredients of the proof? So the proof uses some sophisticated result of the dose, which I believe is from about 10 years ago, about strongly bounded classes of Banach spaces. Okay. And if you combine this with Bourgain's C0 index, okay, together with the fact that the higher order Tyrrellson spaces, so T star alpha, where alpha is a countable ordinal. So these spaces are separable, reflexive, and asymptotic C0. And they have a large Bourgain C0 index. Okay. So when you combine these three ingredients, then you get the theorem. So it's really a laser proof of a nice statement, but and everything pretty much was already in the literature. So I don't think we should get too much credit for that. But the main thing is that it uses this result of the dose really as a black box. I mean, I would not be able to tell you anything that is in those result besides that I can tell you how we use it. But it looks to me that this is quite sophisticated. But the thing, it doesn't, I mean, everything happens there more or less. I mean, half of the work happens there, but it doesn't maybe explains much of why this theorem is true. Okay, it doesn't give you a lot of information, I think. Okay, and the other thing I want to point out here is that this class here is a class of Banach spaces. Okay, but everything else, it's about metric structures. So for me, it doesn't really feels right that you have one foot in the linear world, the other foot in the metric world, and you would like to have something. I mean, at least personally, I would like to have something purely metric. Okay, what is really the metric content of this class that allows you to recover the space C0 inside the metric space Y. Okay. So my main goal today is to show you how we can prove results of this type here in a purely metric setting and not using this sophisticated tool of strongly bounded classes, okay? But only Bourgain's index theory, but in a nonlinear setting, all right? So, so let me state the two theorems that I want to discuss the ingredients in the proof. So the first one is the following. So if for every countable ordinal alpha, I can embed a certain metric spaces. So these are S alpha of Q, which are what I will call Schreier metric spaces. So if I can embed them into a metric space that is a Polish metric space, so it has to be separable, metrizable, and complete, then, well, C0 embeds by Lipschitz into Y dy. Okay. Now, this object is a metric space. Okay, this is a metric space. These metric spaces, they actually embed by Lipschitz in a fairly natural way in the higher order T-Rosen species T alpha star. Okay. And so they are kind of the core structure inside these spaces that capture enough of the structure of C0 when you look at them collectively, allows you to recover the entire C0 in the space. Okay. So this is one theorem, and the second one that I want to talk about is this one. So the first one is in the Lipschitz category. Okay. The second one is in the coarse category. So for every again countable ordinal alpha, so this is a slightly different Schreier metric space. It's not over Q but over Z. I'll get to these differences a little bit later. So if I can embed these metric spaces into Y dy, then C0 coarsely embeds into Y. Now, this is not true. I mean, I don't know if this is true in general. To prove this theorem, we need extra set-theoretic axioms. So what we need is Martin axioms plus the negation of the continuum hypothesis. Okay. So I'm not going to tell you right now why we need that. Maybe if I do a good job explaining the Lipschitz result over here, then I will give you enough hints to maybe to guess how we use Martin axioms plus the negation of the continuum hypothesis for the coarse result. Okay. So I will focus on the Lipschitz result because if you understand this result, then it's going to be easier to see what has to be done for the coarse result. And the new tool that we're using, I mean, it's more like an old tool which has been pushed to the a little bit further. So the key is to introduce a nonlinear ordinal index. Okay, so we have a Lipschitz index, a Lipschitz C0 index for the Lipschitz result, and we have a coarse C0 index for the coarse result. Okay, right. So as I said, this is heavily influenced by Bourgain's work. So let me explain the approach of Bourgain, because it's going to be a lot easier to understand what we're doing then, which has some, I mean, it's a little bit less intuitive, and it's a little bit more cumbersome to write everything down. So I will try to explain very well how Bourgain did, and then to explain to you how you can modify this to make it work in a linear setting. Okay, but the modification is definitely non-trivial. So what is Bourgain's index theory for basic sequences? So if I give myself a metric space, not a metric space, just a set, okay? If I give myself a set, and I will equip, so the set of finite sequences. So I use this notation for the set of finite sequences. So here I include the empty set, okay, when n equals 0, and it's finite sequences, so they can be a repetition. So, and I equip this with the following partial order. So if I look at x1, xn, and if I have y1, yk, so I'm going to say that the x1, xn is less than y1, yk if so n is less than k, and x1 equals y1, xn equals yn. So this is just extension, okay? Extension of finite sequences. So when you equip the finite sequences with this partial order, what you get is that this is a tree in an abstract sense. So which means that the set of, so if you fix a finite sequence and you look at the set of predecessors, this is a finite totally ordered set, okay? And I mean, naturally you want to represent this in a tree fashion, okay? So this is a tree. Now, what we look at more carefully are trees over a set. So a tree over X. So this is going to be, so this is more natural in what Bourgain was doing. So a tree over X, or X is a set, eventually it will be a Banach space, but so it's a subset of the set of finite sequences that is closed under taking predecessors. Okay. So when you do this, you don't want your trees to have holes in there in branches. Okay. All right. And so right now I'm just introducing definitions, and I'm sure some of you know very well these things. I apologize for that, but I think it's important to recall this. So a tree over X is going to be well-founded if there is no infinite sequence. So in X, this is in X, such that so x1, xn belongs to T for every n. Okay, so for an abstract tree, the trees were founded if there is no infinite increasing sequence. Okay. All right. So here, when you look at the tree over X, the tree is well founded if there is no infinite branch. Okay. Now let me just pause for a moment to give an example, and these are related to the Schreier metric spaces that we consider. So the Schreier trees. So here I will look at the set of finite subsets of the integers. So here it's not finite sequences of integer. Okay, it's finite subsets. So I don't allow repetition, and an element in this set is written. Well, it's a set, but let me use the tuple notation. I always write the elements in increasing order, strictly increasing order. Okay. So I will just tell you what is S0 and what is S1, because these are the only two Schreier trees that I can decently draw. So S0, so okay, you can add a root or not. So let me look at rooted trees, but it doesn't make a big difference here. So and you continue like this. So this is going to be S0. So it's a countably branching tree, and the height is 1. So you have 1, 2, 3, and so on, and you continue. Okay, so this is S0. Now S1 is the following tree. So again, you have the root, then you have 1, and that's it. And then you have 2, and then here you're allowed to have 2, 3, and then 2, 4, and so on. And if this is 3, you're going to have 3, 4, okay, 3, 5, and so on. And then 3, 4, 5, 3, 4, 6, and so on, and so on. And you keep doing this. Okay. So which means that you can have sets of size 3 only if the first element is after 3. Okay. And then you stop. So elements of size 2 only if the first element is after 2. Okay. And there is only element of I mean, you cannot have two element subset of size 2, because you want the first element. The first element in your subset tells you how many elements you can have in your set. Okay. So this tree is interesting because it's well, it's well founded. Okay, there is no infinite branch, but you have branches here that are finite but larger and larger. Okay, and so this is for S0, S1, and then you can do S2, S3. So you can do you can define S alpha for any countable ordinal alpha. Okay, but then it becomes impossible to draw already S2. So I will stop at this one here. And here the tree, it's a tree with the canonical order here. Okay. So now something that will be important for us is derivation of a tree. It's over X. So I'm going to define a derivation. So first I'm going to say that, so T is a tree over X, say, so T0 is going to be T. And then the derivative of the tree, I'm going to keep the finite sequences that can be extended. Okay. So which means that I'm removing the maximal elements. Okay. And then if I have alpha be an ordinal, so I'm going to define T alpha plus 1 to be the derivative of T alpha. And T alpha will be the intersection of T alpha. So this is a classical transfinite recursive definition. So if alpha is a limit ordinal, so I'm taking the intersection. So this is not difficult to see that each time you're taking the derived tree, you still get a tree. And this allows you to define the order of the tree, which is going to be the smallest ordinal, such that the alpha's derivative is 0. But this, of course, might not happen, and infinity otherwise. Okay. Now there is an important and classical result here, which is the following. So if T is a closed tree on a Polish space, so separable, metrizable, and complete metric space, then T is well-founded if and only if its order is a countable ordinal. Okay. So here closed is refers to the product topology on the set of finite sequences. Okay. So so this is going to be extremely important for us. So what it says, the way we're going to use it, the way Bourgain used it, is that if the ordinal is at least omega 1, okay, then it means that the tree is ill-founded and that there is an infinite branch. So it says that to ensure that there is an infinite branch in your tree, you need to show that the order of the tree is at least larger than every countable ordinal. Okay. And so what Bourgain did is that he considered the following trees. So if I give myself a Banach space X with a basis EI, so it can be done for basic sequences, but let me just look at a Banach space with a basis. And if I fix a constant greater than 1, and if I give myself another Banach space, okay, I will define T of YXC. I mean, it's really not a Banach space Y, it's about the basis, but to simplify a little bit the notation, let me write X. So you define this as the set of finite sequences such that for every AI, so these are real numbers, you have that the sequence yi is equivalent to the, well, to the initial, let's say, section of the basis EI up to n. Okay. So you look at this. So T, so let me write T to be this. So T is easily seen to be a closed tree over Y. Okay. And the second observation is that T is ill-founded, so which means that it's not well-founded, so it has an infinite branch if and only if, well, I can find an isomorphic copy of the Banach space X, so the Banach space that has a basis, into Y with, well, Banach-Mazur distance C squared. Okay. So this is a straightforward observation. If there is an infinite branch, okay, then there will be a sequence in your Banach space Y that is equivalent to the basis. Okay. And vice versa. So far, so good. And we're going to define the X index as follows. So we're going to look at the supremum over all the C's of the order of the tree over Y X that I defined above. Okay. And an important remark here is the following. So if this index is greater than omega 1, then X admits an isomorphic embedding into Y. Okay. So there is a subtlety here, which is actually going to be important for us later. So why is this true? So if the index is bigger than omega 1, so for every countable ordinal, you will find a constant such that the order of this tree is at least alpha. And then you want an isomorphic embedding. So for some Banach-Mazur distortion. So here, by the pigeonhole principle, so this is an infinite pigeonhole principle. Okay, so we're using the fact that there are uncountably many countable ordinals. So you can find a universal constant C and Y, which is uncountable, such that for every countable ordinal in this Y, the order of Ty x C is greater than alpha. Okay, so just split your non-negative real line with countably many intervals, because there are uncountably many countable ordinals. You can guarantee the existence of this, and this tells you that T of Yx for this C is ill-founded because of the proposition above, and this implies that X and it's an embedding to Y, linear embedding. Okay. So, and what Bourgain did is that he constructed for every countable ordinal alpha a separable reflexive Banach space with a large order. Okay, for which there is a large order here. And this is that in the construction it was definitely not straightforward. Okay. All right, and he did that for the basis. I mean, if you do this for the basis of C of 0, 1, well, then it proves the result. But actually, his proof, I mean, he could do it for any basis. He could construct separable reflexive Banach spaces that contain like this initial segments of any basis. Okay, it's the fact that you have the basis of C0, 1 or not doesn't make any difference. Okay, so this is the general scheme of Bourgain's index theory. Now, so what about a Lipschitz C0 index? Okay, if you want to prove the Lipschitz result. So here, well, looking at trees over a set, okay, and by looking at these finite sequences, this is very natural here because of the linear nature, okay? So you have to compare these sequences. So if you have a basis, you have to compare sequences to this basis. Now, when you're trying to show that a space by Lipschitz embed, I mean, this is not something you can check just on a linear combination of vectors. So you have to do something different here. Okay, you cannot just look at finite sequences. So the way we propose the following solution to this problem. So first, you need a substitute for these finite sequences. So I will call a bunch over a set X. So this is going to be a collection XF, where F is indexed by the following thing here, which I'm going to explain what it is. Where so this is a subset of X, where G is a finite subset of the integers, and what I write bracket G. So this is by definition the set of functions from N to Q, such that the support of F is included in G. Okay. All right. So this will be the substitute for these finite sequences in Bourgain's index theory. Okay. Now I'm going to define a partial order. So the reason I'm taking Q is because in the Lipschitz for the Lipschitz result, if I want to show that C0 embeds by Lipschitz, I just need to show that there is a dense subset that will embed by Lipschitz. So here I can look at rational value functions, and I will put the following partial order on the bunches. Okay. So if this is a bunch, I'm going to say that this bunch is less than this other bunch. So let me use F here. Okay, so the order is defined as follows. So F is an initial segment of G, and XF is going to be equal to YF for every F which is a function supported whose support is in F. Okay, so this makes sense because F is included in G. Okay, so if a function has a support in F, it necessarily has its support in G as well. So I want this kind of extension phenomena as well, but now for bunches. And a vine over X, so it's going to be a collection V of bunches over X, such that, so if psi is a bunch, and if psi is another bunch that is less than psi, then psi belongs to the vine. Okay, so same thing. It has to be stable under taking predecessors, but now it's according to a different partial order. So now, in particular, a vine with this partial order, it's an abstract tree. Okay, so you can define the order, you peel the maximal elements, you can define what it means to be ill-founded, to have an infinite branch and things like that. You can prove an analog of the proposition which says that a vine is well-founded if and only if the order of the vine is a countable ordinal. And same thing, you need some topological assumption on your vine. You need the space over which the vine is defined to be a polyspace. So when things go through, it's just technically a little bit more tedious because of the definition here, which is maybe a little bit less intuitive. But pretty much everything goes through. And then, so do I have 2 more minutes?
Sure, yeah, no problem, go for it.
So, so then we look at vines of the following type. So if you have a metric space, let's say X, and if you give yourself real number greater than 1, so you're going to define the vine over X with this parameter here to be the set of bunches. So in X, such that G is a finite subset of the integers. So that XF, they belong to the metric space. And for every F and G in G here, bracket, so you have the following condition. So you have 1 over C, the norm of F minus G infinity, less than the distance between XF and XG, less than C, the norm of F minus G. So here I look at F, which is a function from the natural numbers into the rationals, as I identify in the canonical way with an element of C0, okay, which has finite support. Okay, so this is a canonical identification. So I look at this, okay, and the C0 Lipschitz index of X, it's going to be the supremum. So this, I mean, it has to be checked, but this is a bind, okay. And so in particular, it's a tree, and I can look at the order of this bind, and I take the supremum over C. Okay. Now here, nothing is really straightforward, as in the case of finite sequences. You have to check that if this index is at least omega 1, then you have a by Lipschitz copy of C0 in it. It's true, it's a little bit more difficult, but not that much to show. And here it's fine because you will do a similar thing. Like if the index is big, okay, so you will have some C alpha for which you have this inequality here. So again, by using the pigeonhole principle, you can find a universal C such that this is true. And then this means that you will have a by Lipschitz embedding of C0 with distortion C squared. Okay. Now, things become a little bit more complicated when you look at the coarse version. So I will just mention what needs to be modified here, and I will stop after that. So for the coarse version, you're going to look at the supremum of the order of the vine. So, but now the vine does not have like one parameter C, it has two parameters, which are the control functions in the coarse setting. And so this condition here becomes rho of norm of x f minus g infinity, and this condition there will become omega of norm of f minus g. Okay, so and here instead of c you would have rho omega. Okay, so that's the only difference in the coarse vine. Now what's the problem here? The problem here is that if the coarse C0 index is large, is greater than omega 1, so for every alpha, you will have some compression function rho alpha and some expansion function omega alpha for every countable ordinal alpha. But here, this completely straightforward trick of using the pigeonhole principle doesn't get you anywhere. Okay. And so, because the pigeonhole principle tells you that in some sense, if you have by Lipschitz embeddings of a family of metric spaces, uncountable family of metric spaces, you have actually an equivalent by Lipschitz embedding. So you can have a universal control on the distortion for an uncountable subfamily. But here you cannot do that. Okay, and that's why we need this Martin's axiom and the negation of the continuum hypothesis. So do you know why? How do we use that? I'm sure the logicians in the audience, they know why we need this. So the reason we need it is because I think a classical and very important consequence of having Martin's axiom plus the negation of the continuum hypothesis is that you have a diagonal extraction principle. Okay, so which we use here to to regularize this collection of coarse embeddings and to get an equicoarse embeddings. I mean, this is roughly speaking. But that's why we need Martin's axiom and the negation of the continuum hypothesis, because it allows us to use an extraction principle. Okay. And I think that's my time is up, so I will stop here. Thank you for your attention, and I'll be happy to answer any questions you may have.
Thanks very much for the talk, for the nice talk. Do you have any questions for Florent?
This principle at the end is not, it's not diamond. I'm really not an expert on all this, but it sounds a little bit like it, some extraction. The diamond principle that's been used in some papers.
I guess it should, I don't know exactly what is the diamond principle, but
okay.
maybe one of these extraction principle I referred to probably has a name because it's so useful, I think. It's so it's about like having like sequences of almost nested infinite subsets of the integers and things like that. So the interesting thing is, I didn't talk about this because I didn't have the time, is that if you don't want to use the Martin's axiom plus the negation of CH, we have some partial result. So if assuming that we don't want to use that, the problem here is that you want to somehow regularize your family of coarse functions, like the compression functions and the expansion functions. So you can do this, but it has some limitation. So which means that in the end, you can only show that your metric space X will contain all the bounded subsets of C0. Okay, so if you don't use Martin's axiom and negation of CH, we cannot prove that you contain C0 if the coarse index, this coarse C0 index is large, but we can show that it contains all the bounded subsets of C0. And when you contain all the bounded subset of C0 in a equicoarse way, by using some barycentric gluing argument, we can embed C0 not into X, but into X to the fourth. Okay, so you need 4 copies of X. And this is due to the barycentric gluing. So to be able to implement this, you need 4 copies of X. So if you don't have these extra set theory axioms, we can show that you contain C0, but not in X, but in X to the fourth. And I don't know if we can get it to X to the third or X to the X squared or just X. I mean, you need probably another idea and a better way to do it, because the barycentric gluing you need to have at least 3 copies, at least, I would say. So, but then you don't use these extra set theoretic axioms.
By the way, for this last thing you mentioned right now, does C0 have anything to do with it? I mean, if you contain all the bounded subsets equicoarsely of another space, then does it mean that it sits inside of the first space?
Yes, I mean, yeah,
or
it's
C0 is important.
So we do it for C0 here, but we're not using pretty much anything of C0. I mean, it's the barycentric gluing. It doesn't have anything to do with C0, for instance. And the definitions of vines as well. I mean, you just change your metric. I mean, you can define it, makes sense. You can get some. I mean, it's very flexible. And something I didn't say during I said I would say something at the end. So why do we need these Schreier sets over Q and Schreier sets over Z? So it's because in the coarse setting, the only thing you need to show is that to coarsely embed C0, you only need to coarsely embed a skeleton. So let's say the integer grid in C0. So that's why we only look at Schreier sets over Z. To embed by Lipschitz's C0, you need to embed a dense subset. So here we need Q because we want something that is dense in it, right? And the Schreier sets, they're just defined as subsets of C0 of vectors whose supports are these Schreier families. That's it. Okay. And these guys, I mean, when you contain them in the vine, I mean, then it means that the order of the vine has to be bigger than the order of the Schreier tree, which is omega to the alpha, coarse alpha. So it really extracts the essence of I would say of the proof. So it's very flexible, I think.
Okay, thanks. Do we have any other questions?
I might just go back to what I said before, and because that question sort of makes sense even in this framework, even if it might be ridiculous. I don't know. Braga, are we still recording, or do you need to
You can stop
go to your
recording.
class, or
Let me stop.
I give you an out if do you teach